Hello, everyone. This is another question that I've gotten several times that I thought I would make a little video on. We're given two charged particles, particle A and particle B, and they are traveling away from the plates that they are of the same polarity as, and they're released at the same time. And we are given their charge magnitudes in relation to each other and the potential energy of A. So without loss of generality, we can just assume that either one of these particles is A and the other one is B until we get to a question about polarities. So just to start, let's write down the form for potential energy from the electric field, and let's interrogate that equation a little bit. So here's what we have. We have that K Q1 Q2 over R is equal to the potential energy. Now, in our case, the potential field is actually a constant because they're in a uniform field. It goes kind of like this. Right? So, since we know they're in a uniform field and the field is constant, we only need Q2. So then what we can say is PEA is equal to it's equal to P QA. So all I did was I turned this KQ over R into this P because we don't need these numbers for now since they're in a uniform field. The second point that we can think about is that since QA is 17 QB, and this is linearly dependent on QA, this is also equal to (17) times QB's potential energy. So solving for the potential energy for B, we get 1/17 the potential energy for A at the initial point. So we can just divide this 37,740 number, or whatever number you have for A, by 17. So, or whatever this value is, by whatever the proportion of A to B is. So that means that we've solved for the potential energy at 0, and the kinetic energy to start is also 0, or is not, it is 0. We've solved for the potential, which is non-zero, and the kinetic energy is 0 at time 0. Let's move on to the second portion of the question. What happens when these are moving? So, before we really get into that, I want to bring you to an analogous set of field equations, which is that of the gravitational field. In Physics 1, we're introduced to this idea that we can calculate the velocity of an object that has fallen a distance h by the conversion of its potential energy at height h into kinetic energy at height 0. So what this is usually formulated as is mgh is equal to 1/2 mv squared. We know that this is the form of kinetic energy regardless. That's the definition. But what happens if we interrogate this mgh quantity a little bit? If I take this mgh quantity and I think about what this is saying, the formula for gravitational potential energy is actually this. Now, when this is a constant, then I get G for Earth times R, the radius of the Earth. So the way this is acting, is as if at the surface of the Earth, I am in a uniform gravitational field that is pulling anything with gravitational attraction downward. That's where this is actually derived from. The H part tells us the change in the potential energy as we go through a height h. And that change in potential energy must then come out as kinetic energy. So if we take this and we generalize it to our plate situation, we also have a uniform field, and we have a linear form for potential energy in relation to kinetic energy from physics 1. So let's assume that we have the same sort of linear form. So let's say now that what we have is QP times D is equal to 1/2 mv squared, which we can just write as KE because we have a linear on this side and it's a lot of work to calculate it on this side, so we don't need to do that. So we've already calculated this. So that means that for a distance traveled, we can subtract off some portion of D and make that the KE. So let's do that real quick. Let's say I've traveled half the distance from plate A to plate B. Then what I have is half of my potential energy has been converted into kinetic energy. So what I can do is I can take potential energy of B over 2 is equal to kinetic energy of B, and that is at 1/2 the distance of D. So then what we can do is we can generalize this. This is a specific example. The potential energy of B at a distance D, or at a distance of a fraction of D, A over B D, is equal to A over B, the potential energy of B at time 0, initial. Which means that the kinetic energy is equal to 1 minus A over B times the potential energy at B. What we can say from this is that this is a conservation of energy problem, and I've written that right here. I'm going to introduce to you a new concept in this formula really quickly, but because the energy is conserved, we can say that given an initial potential energy at a distance of a fraction of D, it has that fraction of potential energy left, and 1 minus that fraction as kinetic energy. So I'm going to erase this, and I'm going to write that out more generally. And I'm going to talk about this quantity. So a lot of you won't get to take classical mechanics because you are in 211, 212. You're probably taking it as a bio major, maybe a chem major. You're taking it as an econ major. You're taking it to get the credit out of the way. A lot of you may be nursing. But physics, this basic physics that you've learned in physics 1 and 2 has had a few centuries of development around it. And one of the most important developments is that all of Newtonian mechanics can be rewritten in terms of energy. So that's what the course Classical Mechanics is about. Uses a lot of calculus. If you're scared of calculus, don't worry about it. It's not that bad. I'm not going to go into calculus. But what we know is that there are two quantities that are really important. One is the Lagrangian and the other one is the Hamiltonian of a system. So we can say that the Lagrangian and the Hamiltonian are conservation of energy statements. And the one that we are concerned with here is the Hamiltonian, which is the kinetic energy plus the potential energy. This term is generally not used for classical mechanics as much as it is quantum mechanics. So you may not hear it as much, but it tells us the kinetic energy plus the potential energy of a system. And what we know is that unless there's some other loss of energy, which in this case there isn't because they're floating sort of in midair, then the Hamiltonian is a constant. So what this means is we can set all of our equations to a constant. And I can make it a function of d. Where d is the distance from its rest state. For our purposes, we don't need any complicated formulation. We can just say that d is just the distance from the rest state plate. Normally, we would want it to be in terms of a radius, which is a vector issue, but we are not concerned with that right now. So then at distance 0, at distance d, where the kinetic energy is 0, so at time 0, we have c is equal to Pe of d plus 0, because it's not moving when we start. So we know that c is just equal to Pe of d, which was, again, that equation that we started off with, which is 1/17 the potential energy of particle A. Now, thinking in terms of what this is at the end, it has no potential energy at the end. All of its potential energy has been converted into kinetic energy in the instant when it hits the plate. So what we see is that c is equal to 0 plus Ke, and this is at d minus d. We have started at d, and we have traveled a distance d, so this is d minus d. It's equal to Ke of 0. So now via this formulation, we can say that Ke of 0 is actually equal to Pe of d. Because it's equal to c here, this is equal to c here, we just move them down. Now the last step is generalizing this to a distance r from the plate. So we have this same c is equal to Pe of d. And let's say we've traveled a distance r. So this is a very general form of this. I'm going to write this as r. I'm going to switch colors so we can see what we're doing. So c of d minus r is equal to PE of D minus R plus KE of D minus R. Well, we know that this is actually just a constant, so we get PE of D is equal to PE of D minus R plus KE of D minus R. Well, we know that this is growing. This is a constant. And this is decreasing, just by the way that the numbers work. So what we can say is that C is equal to the distance D minus R times PE plus R times KE. And this is of distance D. So conceptually, this question is, again, just to drive this back home, this is the same sort of formulation as mgh is equal to 1/2 mv squared for gravitational potential energy. We've traveled a distance h. Since the field is uniform, it is linear in h. And we get out of it 1/2 mv squared in kinetic energy. So for us, what we've done is we have however far we've traveled is proportional directly to our kinetic energy, and however far we are from the origin is proportional to our potential energy, inversely, or negatively proportional. So, let's make sure this makes sense. When D minus R is equal to 0, because R is equal to D, this is 0, and then this is D times KE, so that's correct. So we've got a formulation, and the result is that we can just think of this as our potential energy at a distance is equal to the distance minus the distance we've traveled times our initial potential energy. And our kinetic energy at a distance is equal to the distance times the kinetic energy at the end, which is equal to our initial potential energy. Thank you. Have a good day.